The next thing we're going to talk about are the four basic subspaces associated to a matrix. So let's take a little introductory look at what they are. So suppose I have a matrix A, and it's important that it not necessarily be square. So I have an m by n matrix A. And here's an example, this 2 by 3 matrix. There are some interesting subspaces that I can associate to this. So I can take the rows of A, for example, and I can just take their span. So I take span of 1, 1, 2, 2, 1, 3. That is a subspace of what? It's a subspace, well, these are vectors with 3 coordinates. So this is a subspace of R3. And I indicate subspace with this symbol contained in. This is a subspace of R3 spanned by 2 vectors. Here, on the other hand, if I take the columns, that's another natural thing to do. I can take the span of the columns. So now I have 3 columns, each of which is a vector with 2 coordinates. So this is giving me a subspace of R2. And I'm not going to worry too much at the moment about what subspace it is. I'm just saying that it's some subspace of R2. What else can you do that's natural, a natural subspace defined by a matrix? Well, something that we've seen before, although we haven't thought of it in exactly these terms, is the following. You can consider the null space of a matrix. And that is to say, in our example, you take this matrix and you take the vectors x, y, z such that when you multiply them on the left by a, you get 0. Okay. Now, what's so special about multiplying on the left? We could also multiply on the right. So why don't we take the vectors x, y such that when you multiply on the right, you get 0, 0, 0, like that. That's the 4 possibilities, and those are the 4 basic subspaces associated to a matrix. This one is in R3, and this last one here, it's these matrices, vectors xy with 2 coordinates, so these are in R2. So the subspaces we're getting are 2 of them are in R3, and 2 of them are in R2. Okay, so let's make a formal definition here. So again, we're starting with a matrix A, which is an m by n matrix. Okay, so the important definition, the first one is the column space of A is, by definition, simply the span of the columns of A. Column space of A is the span of the columns. Okay, now let's look at that for a second. This matrix has m rows, so the columns have m entries. So this is a subspace of Rm. Right? These are m vectors, and it's spanned by some collection of n. So some collection consisting of n vectors. It's spanned by n vectors. Now, that doesn't say what its dimension is. It's just telling you that it's spanned by some collection of n vectors. And similarly, the row space is just the same thing where you do it for the rows. The row space of a matrix A is, by definition, the span of the rows. And the rows, of course, are n vectors. So this is a subspace of Rn. And it spans by a collection of m n vectors. Okay? All right. Now, continuing the definition, the null space of A that's the vectors v, which are where? They're in Rn, so that when you multiply them on the left by A, you get AV is equal to 0. And this 0 is the 0 vector, and it's the 0m vector. Because when you multiply an n vector by this m by n matrix, you get an m vector. And I'm going to put in parentheses here the word right, even though usually when I say null space, I'm not going to specify that, because there's a left null space, which is, as I indicated a couple of slides ago, you can do the same thing with the vector on the left. The left null space of A is the vectors V, and now these vectors need to be in Rm so that this operation is defined. I put a vector on the left and I multiply it by A, and I get 0. And now this 0, let's see, let's do a little experiment here. I'm multiplying an m vector by an m by n matrix, so I'm getting an n vector. And I'm asking that this be 0. That's the condition. So that is to say, the 0 that I'm talking about here now is the 0 vector with n coordinates. And I put the transpose up here just to remind you that this is actually a column vector. Being a little bit sloppy with my column vectors and row vectors here. Okay, so where are we? We have these 4 subspaces. What are they again? We have the column space of a matrix. We have the row space of a matrix. We have the null space, or the right null space. And we also have the left null space. And 2 of these are in Rm, and 2 of these are in Rn. I'll come back to that. So let's talk a little bit more about these. A basic fact is that each of these things is, as indicated here, is in fact a subspace of Rm or Rn, depending. And why is that? So why is the column space a subspace of Rm? Well, it's defined as the span of the columns, and similarly the row space is the span of the rows, and anything that's defined as the span of a bunch of vectors is automatically a subspace. So there's nothing more to say there. But let's talk about the null space, or the right null space. So those are the vectors that AV is equal to 0. That is to say, it's exactly the collection of vectors V such that AV is equal to 0. And the claim is that this is a subspace of Rn. Why is that? Well, I have to check. If AV is equal to 0 and AW is equal to 0, does that imply that A times V plus W is 0? Well, it's equal to AV plus AW, which is 0 plus 0, and that's equal to 0. So indeed. And similarly, if you multiply V times a scalar, you can pull the scalar out, and you get C times 0 is still 0. So that checks the properties required of it to be a subspace. I want to revisit these subspaces from a slightly different point of view to draw a picture. So we have our m by n matrix. And remember, that says that you can multiply an n vector and get an m vector. So, and this is important, what this means is that you can think of A as being a function from Rn to Rm. It takes n vectors to m vectors. So let me write that down. That is to say, A can be thought of as a function from Rn to Rm. You plug in an n vector and you get out an m vector. Now it turns out it's a very special kind of function called a linear transformation, which we'll come back to later, but I'm not going to talk about that now. In any event, if you have a map from Rn to Rm, you can take the null space of A as a natural thing. That is exactly the vectors in Rn which go to the 0 vector in Rm. That is to say, the null space of A is the vectors V such that AV is equal to 0. Okay, Now, another natural thing that you can do when you have a map from Rn to Rm is you can look at the vectors in Rm which get hit by this operation. So that is to say, take the image of A, which is another word for the range of A. This is a new definition now. Define the image or the range of A, which is going to be a subspace of Rm, to be the things which you hit. I'm putting two heads on this arrow to indicate they're the vectors which get hit. And what that means is it's the set of vectors of the form AV as V runs over Rn. Take all the vectors in Rn, apply A to them, and see what you get. All of the vectors that A hits. That's clearly a subset of Rm, and it's easy to see that it's in fact a subspace of Rm. So now we have two things. We have the null space of A, which is a subspace of Rn, and we have the image or range of A, which is a subspace of Rm. Now, here is an important fact about all of this, which is this concept that I just introduced, the image of A. Well, it turns out it's exactly the same thing as the column space. So it's not really anything new. The image of A is exactly the same thing as the column space of A, and that is to say, these are the same subspace of Rm. So why is that? So let's just illustrate it with an example. Suppose I asked you for the image of this 2x3 vector. Well, that is to say, by definition, it's all of the vectors that you can obtain by multiplying this by an arbitrary vector x, y, z. And if you do that, what do you get? You get x plus y plus 2z, x plus 3y plus 4z. So the image of this thing is this collection of vectors in R2. These are vectors with two coordinates. And it's a bunch of vectors in R2. And it's a subspace of R2, but how do I see that? Well, if you think about it, you can write this thing as x times 1, 1. Just looking at the coordinates, the coefficients of x over here, they're both 1, plus y times 1, 3, plus z times 2, 4. Okay, so these vectors, which are in the image, which are what I get by varying x, y, and z, it's just the same thing as taking a linear combination of the columns 1, 1, 1, 3, and 2, 4 of the original matrix. So that's it. That's all there is to it. The image is exactly the same thing as the column space, the linear combination of the columns. Okay, so let's draw our picture again. We have this map from Rn to Rm, and A is an m by n matrix. And I have here the null space of A, and I have over here the image of A. And remember, the image, another term for the image is the range. And that's exactly the same thing as what I just said, is it's the column space of A. Okay, now there's another bit of terminology over here on the left-hand side for the null space. It's also called the kernel. I like null space because null sort of tells you what it means, null meaning 0, but also very common terminology is kernel. So we have this nice picture now. We have the subspace of Rn. Those are the vectors such that AV is equal to 0, and we have the subspace of Rm, which is the set of all vectors of the form AV, where V runs over a vector in Rn. Okay, there's a lot of terminology here, so let me just say one thing. The null space and the kernel, which are synonyms, so let me just talk about null space. That's that's a subspace of Rn, and on the other side, the range, or the image, is a subspace of Rm, described by, as I said here. The column space is a little bit different. That's sort of a practical thing. If you're given a matrix, you write down its columns to see what it looks like, but conceptually, the null space and the range are the main definitions. Now, back at the beginning of this lecture, I mentioned that there were 4 basic subspaces. I'm only talking about 2 of them here, one in Rn and one in Rm. Well, one of the other ones, for example, was the row space. And the row space is just the same thing as the column space of the transpose. And the transpose is an n by m matrix. And so though the rest of the subspaces will come into consideration when we bring in the transpose. And I'm not going to do that right now. I'm going to focus on these 2 subspaces for the moment and come back to the others later. Okay, so let's turn now to just a sort of practical question. How do you compute these things? So the image of A, or the range of A, that's the same difference. Well, I've already told you computationally how to handle that. It's simply the column space of A, and you know how to do that. You write down the columns and you take their span. Take the span of the columns. But I think it's worth writing it down in another form. What does it mean for something to be in the range or the image? That is to say, just by the definition, if you have a vector W and it's an M vector, what does it mean for it to be in the range? Well, by definition, it means that you can find a vector v such that AV is equal to W, which is to say the equation AV equals W has a solution. And I'm putting the transpose here just to be consistent about rows and columns. So, for example, suppose I gave you this matrix, the matrix 1 0 0 0 1 1. Is 1 2 in the image of this? Well, I'll answer this question 2 ways. The first is, well, the image is the span of the columns, which is 1 0 0 1 and, well, 0 1 again, so I don't need it. And what is the span of these 2 vectors? Well, all of R2. So every vector every 2 vector is there, so the answer is yes. That's one way to look at it. Another is just to write down the equation. Can I solve this, xyz, is equal to my desired vector 1 2? So you have to solve this equation for xyz, and it's easy to see that you can do that. The vector xyz is equal to 1 1 1 works. So that's another way to see the same thing. So that's a sort of practical way to look at the range. Now let's look at the null space, or kernel, which is the same thing. So how do you compute the kernel of a matrix? Well, remember, V is in the kernel or null space of the matrix A. Well, that's if and only if AV is equal to 0. Well, so you're solving this equation, AV is equal to 0, and you all know how to do that. So, for example, suppose I asked you for the null space of this matrix. That's exactly the vectors xyz, such that this times xyz is equal to 0 0. And that's an equation in xyz that you all know how to solve very well. Well, I've been very nice here. It's already in row echelon form. It's easy to see that the solution is x has to equal 0 and z has to equal minus y. So that is to say there's one free variable, and this subspace is one-dimensional. Okay, finally I want to talk a little bit, say a few more words about the null space and the range. So remember, the null space is a subspace. So the null space of A is, we've already said it's a subspace of Rn. And, well, this is sometimes stated as something called the superposition principle. And this is some fancy words for nothing new. The superposition principle says that if you have two solutions to AV equals 0, which is AV equals 0 and AW equals 0, then you can add them. Which is to say, if you have two solutions V and W, then you can superimpose them and take their sum, and that's also a solution. Well, that's just saying that the null space is a subspace. And so not only can you add them, of course, you can take any linear combination of them. So let me indicate that here. The superposition principle says that if you have two solutions to an equation AV equals 0, then you can take any linear combination of those and still have a solution. So that's just the notion of a subspace. Now let's talk about the range a little bit. So we have this map A from Rn to Rm, and suppose I have a vector B in Rm. So it's this B1 through Bm, and I'm interested in whether B is in the range. Well, remember, that means exactly that I can solve the equation AX is equal to B, where X is a vector in Rn. And we've talked quite a lot about solving such an equation. And there's an important theorem here, which is the following. First of all, B is in the range of A if and only if this equation has a solution. Well, okay, that's just repeating myself. That's sort of obvious. And pick one of those, pick a solution and call it X star. Okay, so you have one solution. Now, the second part of the theorem is the new one, really. So if it does have a solution, then the collection of all solutions is the following. You're trying to find all solutions to AX equals B, and the claim is that they're all vectors X of the form X star plus X naught, where X naught is an arbitrary vector in the null space of A. Okay, so you take this fixed vector X star, which you found, a single solution to AX is equal to B, and then you're allowed to add to it any vector X naught such that AX naught is equal to 0. Okay, so let's take a look at why this is true. So let's see. The main point is like I said, one we've already said several times. Let's look at two. What I want to show is the following. Suppose AX is equal to B. Well, let's see. Let's say we know that AX star is equal to B, and suppose I have another one, AX is equal to B. Well, I'm claiming that then you can write X as X star plus X naught, where X naught satisfies AX naught is equal to 0. That's what I'm claiming. So why is that true? Well, it's pretty obvious from the way I've written these equations. If you take these two equations, AX star is equal to B and AX is equal to B, and subtract them, then what you get is that AX star minus AX on the left-hand side is equal to, well, the right-hand side is b minus b, which is 0. And on the left-hand side, you have a, and you can factor out the a to write it as x star minus x is equal to 0. And there you go. That says that x, the difference of x star and x is in the null space of A. X star minus x is in the null space our kernel of A, which is to say that x star is, x star minus x is equal to x naught, which is to say if you just bring one of those to the other side, you get that x is equal to x star minus x naught. That is to say, x is x star plus this minus this vector x naught. Here I wrote it as plus, but it doesn't matter. You can change the sign on x naught. So that's this basic fact.